Swayam Prabha. Digital India. Educated India.
Hello students, this is Professor Ravin Zugade from Department of Chemistry, Rashtrasanta Tukadoji Maharaj, Nagpur University, and we are discussing about the course of BSc Semester 1 as per BSc Honours Chemistry course of UGC curriculum. And in first 3 lectures we have discussed about the first topic of or first module of this particular course, that is the atomic structure. Now in the second module we are going to discuss about the periodic properties of the elements. This lecture has been prepared under the academic expertise of Professor L.J. Paliwal from Department of Chemistry, Rashtrasanta Tukadoji Maharaj, Nagpur University. So let us start with our discussion on periodic properties. This will be a module consisting of a few lectures covering all the periodic properties. Outline of this particular lecture is periodicity in properties, laws of periodicity, periodic classification of the elements, long form of periodic table, followed by 2 important periodic properties of effective nuclear charge and atomic radius. We will discuss them one by one in a systematic manner. So let us start. What is meant by periodicity in the properties of the elements? Now, initially when the elements were discovered, the very first classification of the elements was as metals and non-metals. Certain elements possessing certain important or distinct properties like luster, moldability, they were classified as metals. They were having good shine. Whereas those elements which lacking this type of properties or these properties, they were classified as non-metals. So this was the very early classification of the elements. But when the new elements were discovered, it was found that some of the elements do not come under metal category or typical non-metal category. So discoveries of the new elements found that this particular classification is insufficient, and as a result the people or scientists started thinking to classify the elements in different manner. Various attempts were made from early 19th century till date, and the early classification of the elements started in early 19th century with the attempts made by Dobereiner, Newlands, then followed by Mendeleev in the 19th century, and at the beginning of 20th century the attempt made by Moseley to classify the elements. So early attempts with Dobereiner triads and Newlands octaves. New foundation of the modern periodic table or modern periodic law was based on various attempts made over a century of efforts by various landmark scientists. We are going to discuss them in a chronological order to see how the periodicity in the properties of the elements have been evolved over a century of efforts by the physicists as well as chemists. The very first scientific attempt to classify the elements on the basis of periodic properties was put forward by Dobereiner, who was a German chemist, and the studies started in early 19th century. In 1817, he put forward the law of triads. What Dobereiner did, he collected or selected the elements having identical properties. So if you have a group of 3 elements with identical properties, they were called as triads, and Dobereiner arranged these triads in the increasing order of their atomic masses, and he came up with a law which can be stated as when elements with similar properties are arranged in the increasing order of their masses, then the mass of the central element is arithmetic mean of that of the other two elements. We will see, or we will try to explain this on the basis of actual examples. Consider the first triad, which is of lithium, sodium and potassium. Now these three elements, we know that they are having identical properties. They are metallic with low ionization potential, and they are typically soft metals. Now the atomic mass of lithium is 7, sodium is 23 and potassium is 39. Now if we add the extreme two element masses, then it will be 39 plus 7 will be 46, and arithmetic mean of these two is 23, which is equal to the atomic mass of sodium. So what Dobbe-Reiner stated is found to be correct for this particular triad. Similarly, various other triads were found, and it was observed that the central element has a mass which is approximately equal to the arithmetic mean of the other two. However, it was found that it is not exact mean for most of the cases, and secondly, only 5 such triads were identified. 5 triads means only for 15 elements, whereas at that time around more than 50 elements were known, and so this could not be applied to all the elements which were known at that particular time, and hence the further development in this field was required. Milestone attempt was made by a British chemist in 1864 named Newlands. This Newlands Octaves concept was put forward. According to this concept, when elements are arranged in the increasing order of their atomic masses, then every 8th element has identical properties as that of the first one. So 8th element will have identical properties. Let us try to understand what Newland did. He arranged all the 62 elements known at that time. We are talking about 19th century. Now the known elements are more than double of this, but that time 62 elements were known. And what he did, he arranged the elements in the increasing order of their atomic masses, like hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, followed by sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. Now if we see this lithium and sodium, now if we start from lithium, so 1, 2, 3, 4, 5, 6, 7 and 8th element is sodium, which is having identical properties as that of lithium. If we start from beryllium, the 8th element is magnesium, which is having identical properties as that of beryllium. If we start from boron, 8th element is aluminium, which is having identical properties as that of boron. So this Newlands Octaves rule is found to be valid over a wider range of elements as compared to Dobbe-Reiner triads. If you observe carefully, you will find that there are no noble gases in this particular case. For example, hydrogen is there but helium is not there. Then fluorine is there, but after fluorine neon is not there. Chlorine is there but argon is not there, because these elements were not known at that time. So every 8th element was found to have identical properties as that of the first one. So this is what is called as octaves. So a group of 8 elements, and found to be successful over a wider range of elements. However, this further failed with discoveries of new elements. Person named Mendeleev, he put forward a periodic law in 1872, and this was the very first attempt to put all the elements in a single table called as a periodic table. Now according to Mendeleevs law, the properties of the elements are periodic functions of their atomic masses. So what Mendeleev did, he put all the elements in a single table, and this was the first attempt to put the elements in a single tabular format, and those elements which are having identical properties are put in single group. For example, the Mendeleev periodic law has put the element into 8 different groups, group 1, 2, 3, 4, 5, 6, 7 and 8, and the elements were placed in horizontal rows called as the periods. So period 1, 2, 3, 4, 5, 6. And the elements having identical properties, they belong to same group. For example, if you see that lithium, sodium, potassium, copper, rubidium, silver, cerium and gold, they have identical properties, so they have been put into a single group. So this type of classification was put by Mendeleev. However, again there were certain problems because there were certain gaps in between and the positions of certain elements were not appropriate according to their atomic masses. Hence, further development was required in this periodic table. Now we come to what is called as the modern periodic law put forward by Henry Moseley. Now Henry Moseley was a British chemist and he put forward this law at the age of 25 in 1914. According to Moseley's law, or what is called as a modern periodic law, the properties of the elements are the periodic functions of their atomic numbers and not the atomic masses. And Moseley put 75 known elements at that time into a single table in the increasing order of their atomic numbers, and he called these columns as the groups, and the last column was called as a zero group, which included all the noble gases, because during that time noble gases were invented and they were put in a zero group. So group 1 to 7 and a zero group for the noble gases. Now around 75 elements were arranged in a systematic manner, and all the discrepancies in the Mendeleev periodic table were completely removed in the modern periodic table put forward by Moseley. But unfortunately, at the age of 27, Henry Moseley, he actually died in a war which was actually World War I at the age of 27. So this was found to be, or this was called as one of the greatest loss to the scientific society, because at the age of 27 he died, and before that he put forward an extremely important law which was used to build the modern periodic table, or what we call today as the long form of periodic table. Now this long form of periodic table is based on Moseley's periodic law, and this was used to construct a complete table of elements known as modern periodic table or long form of periodic table. Here all the discrepancies observed in the Mendeleev periodic table were overcome, and this periodic table has 18 vertical columns called as the groups and 7 horizontal rows, that is called as the periods. Lanthanides and actinides, they are placed separately at the bottom of the periodic table as shown over here. We can see that there are 18 vertical groups and 7 horizontal columns, and at the bottom of the periodic table the lanthanides and actinides have been placed. Now all the known elements at that time also and all the known elements even today, they can be placed systematically in this periodic table, and that's why it is called as the modern periodic table. And since it involves all the elements in the nature, it is a long form of periodic table. Now In this periodic table, the elements have been classified on the basis of the position of last electron. We know that the properties of the elements that follow a repetition pattern, they are called as the periodic properties. Now, according to Moseley periodic law, the periodic properties vary in a periodic fashion because of the atomic numbers of the elements, and the periodicity in the properties can be attributed to the outer electronic configuration of the elements. The elements having identical outer electronic configuration or valence shell configuration, they show identical properties. And on the basis of the outer electronic configuration, it is possible to classify the elements into 4 types. The first type of elements where the valence or distinguishing electron or the last electron enters into S subshell, they can be classified as S block elements. So S block elements are those elements where the last electron enters into S subshell. Similarly, on the basis of last electron entering into P subshell, the electrons are classified as P block elements. Those elements where the last electron enters into D subshell, they are D block elements, and those elements where last electron enters into F subshell, they can be classified as F block elements. So this is what we call as a periodic classification of the elements depending on their position of last electron entering into a particular subshell. On the basis of this, if we try to put the elements, we know that S subshell has a capacity of only 2 electrons, and so S block elements occupy 2 groups in the periodic table, and they are placed on the extreme left side. P block elements occupy the extreme right side of the periodic table. Since P orbital or P subshell has a capacity of 6 electrons, there are 6 groups in the periodic table where the P block elements have been put. So there are 6 groups for P block elements. D subshell has a capacity of 10 electrons, and so D block elements occupy 10 groups in the periodic table, and these 10 groups are sandwiched between the S and P block elements. And F subshell has a capacity of 14 electrons, and so these F block elements occupy 14 groups and they are placed inside the D block elements. We will see how these elements have been put in the periodic table. So if you see that on the extreme left side, there are S block elements occupying only 2 columns because S subshell has a capacity of 2 electrons. P block elements occupy 6 groups because they have a capacity of 6 electrons. Similarly, D block elements occupy 10 groups and F block elements occupy 14 groups, and these F block elements are actually lying over here in between the D block elements. Now there is only one S block element which is placed on the extreme right side, which is helium. The position is because of the noble gas configuration and noble gas properties of helium. This is what is called as the periodic classification of the elements. Now we will discuss various periodic properties, starting with screening effect and effective nuclear charge. Now we know that in an atom, the electrons are held in fixed shells or particular orbits due to attractive force of the nucleus, and this force of attraction depends upon the nuclear charge. The nuclear charge experienced by all the electrons is not equal because of 2 reasons. First reason, each electron is at a different distance from the nucleus, and we know that as the distance between the 2 charges goes on increasing, the force of attraction goes on decreasing. So if an electron is present close to the nucleus, then it will experience more force of attraction, whereas if it is present away from the nucleus, then it will experience less force of attraction. Secondly, the attractive force exerted on the outer electrons is partially reduced by the repulsive force exerted by the inner shell electrons. We'll try to understand this in further slides. Consider that decrease in the attractive force exerted by the nucleus on the valence shell electrons due to presence of inner shell electrons, what we call as intervening electrons, is called as the shielding effect or screening effect. And because of the screening effect, there is a decrease in the force of attraction between the nucleus and outer shell electron, and this is because of the screening of the outer shell electrons from the nucleus because of the presence of the inner shell electrons, and the extent of screening can be calculated in terms of the screening constant, which is denoted by a symbol sigma. The effective nuclear charge is calculated by subtracting the screening constant from the total nuclear charge. Suppose, consider this nucleus with a positive charge and an electron is revolving in the first shell. Now, there is a direct force of attraction between the nucleus and the first shell electron. So, the force of attraction experienced by the electron in the first shell is maximum. But if the electron is present in the second shell, then two things have taken place. The distance between the nucleus and the electron is increased, and secondly, there are these two electrons in the first shell which are present in between the nucleus and the outermost electron, and hence these two electrons shield the outer electron from the force of nucleus. This is called as the shielding effect, which can be measured in terms of screening constant or shielding constant. In other words, the intervening electrons are acting as a shield between the outer electron and the nucleus. This screening constant leads to reduction in the effective nuclear charge which is experienced by a particular electron, and this effective nuclear charge is equal to the total nuclear charge minus the screening constant. Okay, so it means that, in other words, we can put it like this: every electron will experience different effective nuclear charge depending on its position in various shells and subshells. How much is the quantitation of this effective nuclear charge and the screening constant? That is put forward by Slater, and according to Slater's rule, we will see how to calculate the screening constant, and by subtracting the screening constant from the total nuclear charge, we can calculate the effective nuclear charge experienced by any electron which is present in an atom. According to Slater rule, number 1, first we have to write the electronic configuration of atom in a particular manner, like 1s, then a group of 2s and 2p, then a group of 3s and 3p, then a group of 3d, then a group of 4s and 4p, then a group of 4d and 4f, and so on. In short, we can classify, or we can go on increasing the principal quantum number 1, 2, 3, 4, etc. and we are clubbing S and P together, D and F together. Secondly, electrons in any group on the right side of the given electron or the electron under consideration does not contribute to the screening constant. For example, if I want to calculate the screening constant for 4s electron, then the electrons which are present in 4d and 4f will have no contribution to the screening constant. Another example, if I want to calculate the screening constant for 2s electron, then 3s, 3p, 3d, 4s, 4p will not have any contribution to the screening constant. It's quite obvious because these electrons are not present between the 2s electron and the nucleus. So only those electrons which are present in between, they will contribute to the screening constant. Thirdly, all the electrons in the same group contribute 0.35 each. For example, if I want to calculate screening constant for one electron in 3s and 3p, and this group contains suppose 4 electrons. So 1 electron is under consideration. Remaining 3 electrons will contribute 0.35 each to the screening constant. Fourthly, all the electrons in n-1 shell will contribute 0.85 each. Take an example. If I am talking about one electron which is present in 3s orbital or 3p orbital, then all the other electrons present in the same group will contribute 0.35 each, and those electrons which are present in the second shell, which is n-1 shell, will contribute 0.85 each. Thirdly, all electrons in n-2 and lower shells will contribute 1 each. So their contribution will be unity. Okay. And if the electron under consideration belongs to D or F subshell, then rule number 4 and 5 are invalid, and all the electrons in the groups on the left side contribute 1 each. These are Slater's rule to calculate the value of sigma, which is screening constant. Now we will try to understand these rules with the help of some examples. Take how to calculate effective nuclear charge for various electrons in different atoms. Suppose we want to calculate the screening constant and effective nuclear charge for 3s electron in magnesium. Now, the electronic configuration of magnesium is 1s2, 2s2, 2p6 and 3s2. Now we are interested in 3s electron. So electron is present over here. Now we are considering one electron among these 2 electrons which are present in 3s subshell. Okay, now according to Slater's rule number 1, we have to write the electronic configuration in the form of the groups like 1s, 2s2p and 3s3p. There is no need to write the remaining groups like 4th and 3d. So if we write the electronic configuration, 1s has 2 electrons, 2s and 2p combinedly have 8 electrons, and 3s and 3p have combinedly 2 electrons. Out of these 2 electrons, 1 electron is under consideration and 1 electron is other than the one under consideration. So number of electrons in the same group except the one under consideration is equal to 1, and all the electrons in the same group contribute 0.35 each, and since there is only one electron, so the contribution of the electron from the same group is equal to 0.35. Next is number of electrons in the n-1 group, that is now nth group is third shell, so n-1 will be second shell, and in second shell there are 8 electrons which will contribute 0.85 each. So 8 into 0.85 will be 6.8. Number of electrons in the n-2 group, that is first shell, there are 2 electrons and they will contribute 1 each, and so the contribution from 1s group is coming out to be 2. Now we will add these 3 together, 0.35 plus 6.8 plus 2 comes out to be 9.15, which is the screening constant sigma for the 3s electron in magnesium. And if we subtract this value of sigma from the total nuclear charge, which is equal to the atomic number Z, then the effective nuclear charge comes out to be 2.85. What is the meaning of this? The meaning of this is that even if the total nuclear charge is 12 positive charges, by the time it reaches to the 3s electron, the force which is experienced by the 3s electron is only 2.85 positive charges. Let us see another example where we will consider some electron in the p subshell. So let us see, calculate screening constant and effective nuclear charge for the 3p electron in silicon. Now this is 3p electron, which is the valence electron in silicon. We will move ahead in the same analogy, in the similar steps as what we have followed in the previous example. So let us start with writing the electronic configuration of silicon in a regular manner. Silicon with atomic number 14, electronic configuration will be 1s2, 2s2, 2p6, 3s2 and 3p2. So we want to determine the effective nuclear charge which is experienced by the electron which is present in 3p subshell. Now, writing the electronic configuration according to Slater rule number 1 in the form of various groups like 1s with 2 electrons, 2s and 2p together with 8 electrons, 3s and 3p together with 4 electrons. Now out of these 4 electrons, 1 electron is under consideration for which we want to calculate the effective nuclear charge. So remaining electron except the one under consideration in the same group 3s 3p is equal to 4 minus 1 electron under consideration will be equal to 3. So these are the 3 electrons which will contribute to the screening constant, and contribution of the electrons which are present in the same group is equal to 3 into 0.35. So contribution of each electron is 0.35 and there are 3 such electrons, and hence the total contribution of these 3 electrons to the screening constant comes out to be 1.05. What are the other remaining electrons? So number of electrons in the n-1 group. So nth shell is the third shell. So n-1 group is the second shell, and there are 8 electrons in the second shell or in this particular group of 2s2p. And since there are 8 electrons, each of them will contribute 0.85 according to Slater rule, and so the total contribution of these 8 electrons again comes out to be 6.8. Similarly, there are 2 electrons in the n-2 group. N-2 group is 1s subshell, and so there are 2 electrons and each of them will contribute 1 each, and as a result total contribution from this 1s group electrons is equal to 2. Adding these 3 together, the total screening constant sigma is the sum of these 3 values, comes out to be 9.85. Now subtracting this value of 9.85 from the total nuclear charge, which is equal to the atomic number, comes out to be 4.15. Now this 4.15 is the effective nuclear charge experienced by the 3p electron present in silicon. Hence, in short, what we can summarize is, even if the nucleus is having 14 positive charges or the value of Z is 14, the actual force experienced by the last electron is coming out to be only corresponding to 4.15 positive charges. Let us take one more example where the electron belongs to d subshell, because the rule is different for d electrons, because d orbital is diffused and it experiences more or enhanced screening effect by the inner shell electrons. Let us take an example of effective nuclear charge for 3d electron in nickel. Now in case of 3d electron, now this is a d block element, nickel is a d block element with atomic number 28 electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and then 3d8. Okay, now writing the electronic configuration in the form of Slater's rule. So you have 1s, 2s2p, 3s3p, 3d and 4s4p. Now according to Slater rule, the 4s and 4p, these subshells or these two subshells are outside 3d and electron under consideration is in 3d. Hence, those electrons which are outside will definitely not contribute to the screening constant. So the contribution of these two electrons is 0. Next is, what about the contribution of the other electrons which are present in the same group? Now, which element or which electron we are interested in? We are interested in the 3d electron. There are 8 electrons in 3d. Out of that, 1 is under consideration. So number of electrons except the one under consideration comes out to be 7. And these 7 electrons will contribute to the screening constant as at a rate of 0.35 each. Multiplied by 7 will come out to be 2.45. So this is contribution of 3d electrons. Now since the electron under consideration is in 3d subshell, all the electrons on the left hand side of these will contribute 1 each according to Slater rule. And hence for d electrons, whatever electrons are present on the left side groups, so these 2 plus 8 plus 8, that is equal to 18 electrons contributing 1 each. So total contribution of these electrons is coming out to be 18. So the total contribution of all the electrons comes out to be this 18 plus 2.45 coming out to be 20.45. This is the screening constant sigma. Subtracting this screening constant sigma from the total Z value coming out to be 7.55. In other words, the force experienced by the 3d electron in nickel corresponds to only 7.55 positive charges, even if the total positive charge on the nucleus is 28. But by the time it reaches to the 3d electron, because of the screening effect of the inner shell electrons, the net effective charge experienced by the 3d electron comes out to be 7.55 only. This is how the effective nuclear charge can be calculated by using Slater's rule. Now let us see how the effective nuclear charge varies in a periodic table. We know that periodic table consists of horizontal periods and vertical groups. Now first we will discuss the variation of effective nuclear charge along the horizontal period when we move from left to right. So when we move across the period from left to right, there are a few factors which get changed. The very first factor which is affected is the atomic number, and for every element the atomic number goes on increasing by 1 unit. Consider an example of say lithium. Lithium has atomic number 3. From lithium to beryllium, atomic number increases by 1 unit, thereby the nuclear charge Z increases by 1 unit each. At the same time, the electrons are added in the same shell, and so screening constant sigma increases by a factor of 0.35 as per the Slater's rule. Okay, so if we consider this atom with lithium having positive charges 3 in the nucleus, so nucleus is tripositive and there are 2 electrons in the first shell and 1 electron in the second shell. When we move from lithium to beryllium, the atomic number increases by 1 unit and electron is added to the same shell, that is second shell. When we move to the next element, boron, atomic number increases to 5. The positive charges in the nucleus become 5 and electrons are again 5. 1 electron which is added to the same shell. Now the added electron is contributing 0.35 to the effective nuclear to the screening constant, thereby reducing the effective nuclear charge by a factor of 0.35, whereas Z is increasing the effective nuclear charge by a factor of 1. Similarly, when we move to next element, the electrons are added to the same shell and the positive charge in the nucleus goes on increasing. Every time the increase in the nuclear charge, Z value is by 1 unit and sigma value is by 0.35 unit. Net effect is there is ultimate increase in the effective nuclear charge by a factor of 0.65, because we know that effective nuclear charge Z star or Z asterisk is equal to this Z minus sigma. Every time Z is increasing by 1 unit, sigma is increasing by 0.35, thereby the value of Z star, that is the effective nuclear charge, will go on increasing from left to right in a period in the periodic table. Now, what happens to this effective nuclear charge down the group? So when we move from first period to second period to third period to fourth period down the group, again some variations take place. The very first thing which takes place is a large increase in the atomic number, that is Z, or the nuclear charge Z. So that goes on increasing continuously when we move down the group. Secondly, the number of shells are continuously increasing. So new shells are added, leading to large increase in the screening constant. So two things are increasing. The Z value is increasing and screening constant sigma is also increasing. Consider this example of, say, hydrogen. Hydrogen is having only one shell with one electron and one positive charge in the nucleus. When we move down the group for lithium, nucleus is having 3 positive charges, but one extra shell is added. So now the last electron is in the second shell. So number of shells is increased. As a result, the value of sigma is increased. Similarly, when we move down further to sodium, one more shell is added. So every time this screening constant is increasing, and also the distance of the electron from the nucleus is also increasing. As a result, the net effect is decrease in the effective nuclear charge, that is Z asterisk, down the group. So when we move down the group, the effective nuclear charge goes on decreasing. When we move across the period, the effective nuclear charge goes on increasing. This is the effect of change in effective nuclear charge down the group and across. Okay, so this is about the first periodic property which we have discussed, that is the effective nuclear charge and screening constant. Coming to the second periodic property, that is atomic radius. Now, how will you define an atomic radius? We know that atom is generally assumed to be spherical in shape, and as a result, we can measure its size in terms of radius, since we assume it to be a spherical structure. And the atomic radius can be defined as the distance of the outermost electron from the center of the nucleus. So from nucleus to the valence shell electron or outermost electron, that distance we call it as the atomic radius. However, it is not possible to determine this atomic radius experimentally exactly. There are a few reasons or few difficulties in exact experimental determination of atomic radius. The first difficulty is atom is extremely small and it is not possible to isolate the atom. That is a problem. So experimentally we cannot calculate the distance between the nucleus and the outermost electron. Secondly, the position of electron is also uncertain. We have discussed in case of Heisenberg uncertainty principle that it is impossible to determine the exact position of the electron, since it is a microscopic particle in motion with extremely small mass. Hence, it is not possible to determine the position exactly. And thirdly, the electron density around the atom is affected by presence of neighboring atoms. Whenever any atom comes in close proximity of some other atom, it affects the atomic electron density or electron charge density, and as a result, for one particular compound, the radius will be different. For different compound, the radius will be different because of the effect of the other atom which is associated with the atom under consideration. So these are the problems with atomic radius determination in the experimental manner. Due to these difficulties, the atomic radius is generally expressed in different ways, or there are indirect ways of expressing the atomic radius. The first way of expressing the atomic radius is the covalent radius. Now, as the word is indicating, it is related with the covalently bonded compounds. Now, the covalent radius is defined as half of the internuclear distance in a homonuclear diatomic molecule. Let us try to understand the meaning of each and every word. What is a homonuclear diatomic molecule? Now, those molecules which are diatomic means contain two atoms, and homonuclear means both the atoms are identical. For example, H2 molecule, Cl2 molecule, N2 molecule. So these are the homonuclear diatomic molecules. And for such molecules, half of the internuclear distance is called as the covalent radius. For example, if we consider H2 molecule, now for H2 molecule, it is practically possible to determine the distance between the two nuclei, because nuclei are having larger mass and it is not affected by the Heisenberg uncertainty principle, or there is no uncertainty involved or almost negligible uncertainty involved in the location of the nuclei, because it is not in motion, and the mass of nucleus is much larger than the mass of electron. So experimentally it is possible to determine the bond length of H2 molecule, and half of the bond length is considered as the covalent radius. Hence, in this particular case, the bond length of H2 molecule is 0.74 angstrom. Thereby, the covalent radius becomes 0.37 angstrom. Another example is Cl2 molecule. Now, for Cl2 molecule, the bond length of Cl-Cl bond is 1.98 angstrom. Hence, the covalent radius of Cl atom is half of that, which is equal to 0.99 angstrom. Second way of expressing the atomic radius is the ionic radius. Now, what is the ionic radius? It is the distance between nucleus and a point of influence of the nucleus on the electron cloud. Now, we know that every ion or atom consists of a positively charged nucleus and the electron cloud. The distance up to which the nucleus has got its effect, that distance is called as ionic radius. It can also be expressed in a different manner, like radius of monoatomic ion in an ionic crystal structure. Now we know that in case of ionic crystal, the ions are close packed, and since they are close packed, we can calculate the ionic distance or monoatomic ion. For the monoatomic ion, the radius can be calculated. So in case of ionic crystal structure, whatever is the radius of monoatomic ion, that can also be called as the ionic radius. For example, if we consider this cation and anion forming a solid ionic crystal, in solid state, they are externally touching each other, and so this radius is called as the cationic radius, and this will be called as the anionic radius. Now, cation is formed by loss of electrons, and so the size of the cation is less than the corresponding atom. For example, if we consider sodium atom and sodium Na positive ion, in that case, one electron is lost. Now, electron is lost, but the nuclear charge is same. As a result, the force of attraction of the nucleus per electron increases, and as a result the cation has smaller radius as compared to the corresponding atom. On the other hand, exactly opposite manner, anion is formed by gain of electrons, and so there it is larger than the atom because one extra electron is added and nucleus have same charge as that of the atom. As a result, the force of attraction experienced per electron decreases, hence anion is larger in size as compared to the native atom. Third way of expressing the atomic radius is the metallic radius. Now in case of metals, we know that the atoms are externally touching each other in the solid state, and hence half of the internuclear distance in the solid metallic crystal is called as metallic radius. For example, if we consider any metal like copper, nickel, sodium, even the iron, so any metal, whether it is transition metal or alkali or alkaline earth metal, half of the internuclear distance is taken as the metallic radius. These metals are close packed and hence it is possible to calculate half of the internuclear distance. Fourth is the van der Waal radius. Now we have discussed three types of radii. First is a covalent radius. Now this can be calculated experimentally for those molecules which form covalent bonds like H2 molecule, Cl2 molecule, N2 molecule, which are covalently bonded. Similarly, for ionic radius, it is possible to determine the ionic radius for those atoms which form ionic bonds like sodium chloride, cesium chloride, potassium chloride, calcium chloride, etc. Metallic radius can be calculated for those metals or those elements which are metallic in nature and the metal crystals are available. But if any of these is not available, in that case the van der Waal radius is expressed. Now this is defined as half of the distance between two unbonded atoms when electrostatic forces between them are balanced. Let us try to understand this. This is one example where this is one molecule and this is second molecule. Now these two molecules, when they start coming closer to each other, they cannot come closer than a particular distance. So from here, whatever is the distance between the nuclei of these two unbonded atoms, that is actually the van der Waal distance, and half of that is called as the van der Waal radius. So this is the closest possible approach of the two molecules. In other words, if the two atoms are not bonded, the closest possible distance is taken and half of that is called as the van der Waal radius. Now this radius plays a very important role for those molecules or those atoms which are single atom molecules or what we call as a monoatomic molecules like noble gases. For example, helium atom is there and we want to determine the atomic radius of helium or neon or argon. Now they do not form a compound at all. As a result, it is not possible to determine their covalent radius or ionic radius or metallic radius. In that case, the van der Waal radius is determined. So if this is a helium atom, this is another helium atom, this is the closest possible approach of the two. They cannot come closer than this, and half of the internuclear distance at this particular point is taken as the van der Waal radius. So this concept plays extremely important role for those molecules which do not form bonds or those atoms which do not form bonds. Now let us compare the various types of atomic radii we have discussed. First comparison, let us compare the covalent radius with metallic radius and van der Waal radius. Now covalent radius is always less than the metallic radius which is always less than the van der Waal radius for the same atom. Let us see why. Now when we talk about a covalent radius, we are talking about covalently bonded atoms. And these covalently bonded atoms have overlapping because covalent bond is formed by overlapping of atomic orbitals As a result, if you take half of the internuclear distance between these two, that will be smallest. When we come to metallic radius, the atoms are externally touching each other. And so, if we take half of the internuclear distance between these two, this is definitely greater than the covalent radius. And in case of van der Waal radius, the atoms are slightly away from each other, not touching each other. And as a result, if we take half of the internuclear distance between these two, this van der Waal radius will be definitely greater than the metallic radius. This is a comparison between the three types of radii. Another comparison can be cation radius, anion radius and atomic radius. Now these can be arranged in the increasing order, as cation radius is smaller than atomic radius is smaller than the anionic radius. The reason is we know that cation is formed by loss of electron, so force of attraction is more. As a result, there will be decrease in the size, or the cation gets shrunk because of the nuclear force as compared to atom, whereas anion is larger in size because it is formed by the gain of electrons. So because of one extra electron, the anionic radius is generally larger. One more aspect is there. This anion is generally formed by gaining of electron leading to noble gas configuration. Most of the anions we will find that, like fluoride, chloride, oxide, sulfide, they have noble gas configuration with valence shell completely filled, and so there is a larger interelectronic repulsion because of the completely filled valence shell, and this leads to increase in the radius. On the other hand, cations are formed by loss of electron, and if the valence shell electrons are completely lost, for example in Na converting into Na positive, in that case one complete shell is reduced. So Na has a valence shell in 3s subshell, whereas Na positive has a valence electron in the 2p subshell. Hence there is a reduction in the size, and in case of anion there is a enlargement in the size. What are the factors which govern the atomic radius? The very first factor which governs the atomic radius is the nuclear charge. Now, if you have an atom with a positive nucleus and an electron revolving around it, now when the nuclear charge increases, what will happen? The outermost electron will get attracted closer to the nucleus, and as a result, with increase in nuclear charge, the atomic size will decrease, or atomic radius will decrease. In other words, we can say that the atomic radius is inversely proportional to the nuclear charge. With increase in nuclear charge, the atomic radius will decrease, or with decrease in nuclear charge, atomic radius will increase. Second factor which governs the atomic radius is the number of shells. Now, if you have an atom with one shell, you have an atom with two shells, you have an atom with three shells. With increase in the number of shells, definitely the distance between the nucleus and the outermost electron goes on increasing, and as a result, we can say that atomic radius goes on increasing with increase in the number of shells. Thirdly, the shielding effect or screening effect. We know what is screening effect. Screening effect is the force of attraction between the nucleus and the electron which is present in various shells and subshells. Now when you go away from the nucleus, the screening effect goes on increasing, and screening effect leads to reduction in the attractive force. So when screening effect increases, definitely the force of attraction between the nucleus and the electron goes on decreasing, and hence atomic radius goes on increasing. So atomic radius is directly proportional to shielding effect or screening effect. So atomic radius is directly proportional to number of shells and screening effect, and atomic radius is inversely proportional to the nuclear charge. Now let us see how the atomic radius varies in a periodic table across the horizontal period and down the group. So first, let us see the variation of atomic radius across period from left to right. So when we move from left to right in a periodic table, there are certain variations which are taking place. The first variation is nuclear charge goes on increasing because for every next element the atomic number increases. So we know that nuclear charge increases means atomic radius should decrease because it is inversely proportional to the nuclear charge. Secondly, number of shells remain constant because across any period the electrons are added to the same shell. So we know that with increase in number of shell atomic radius increases, but since the number of shell remain constant, it will not have any effect on the atomic radius. Thirdly, shielding effect increases by very small amounts because electrons are added to the same shell, and so the contribution to the effective nuclear charge is not very significant. As a result, atomic radius will have the major impact of only the nuclear charge, which goes on increasing, and hence atomic radius goes on decreasing across any period from left to right. What happens to the atomic radius for second period elements? When we move from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine, the atomic radius consistently goes on decreasing, as we can see in the values which are given in angstrom units or in the picometer units in this particular graph. So there is a regular decrease in the atomic radius due to increase in the nuclear charge. Now let us see how the atomic radius varies down the group. So when we move down the group from first period to second period to third period, there are certain changes taking place. The first change is the nuclear charge goes on increasing continuously, and this is quite obvious because the atomic number is increasing. Number of shells go on increasing because when we go from first period to second period to third period to fourth period, one extra shell is added every time, and the shielding effect also increases because a new shell is added, meaning that the number of shells or number of electrons which are present between the nucleus and outermost electron are continuously increasing. Because of the combined effect of the two factors favoring the increase in atomic radius, the atomic radius goes on increasing down the group from first period to seventh period. See an example. In case of the first group element from lithium to cesium, the atomic radius is consistently increasing. Similarly, for the halogens, atomic radius is consistently increasing from fluorine to chlorine to bromine to iodine to astatine. This is shown diagrammatically for both these series of elements, group 1 and group 17. This is overall effect of atomic radius. If we see for any period from lithium to neon, sodium to argon, potassium to krypton, etc., we will find that there is a decrease in atomic radius in each period and there is an increase in atomic radius down the group. This is a schematic representation of atomic radius across the period continuously decrease, across the group or down the group continuous increase. An interesting thing can be observed over here. We'll find that the last element has slightly larger atomic radius as compared to the previous one. The reason is interesting that when we consider the noble gases, we are talking about the van der Waal radius, whereas when we talk about all the other elements, we talk about the metallic radius or the covalent radius. And we know that van der Waal radius is always larger than the metallic as well as covalent radius. This is all about this lecture 2 on module 2 of our inorganic chemistry semester 1 course. We will discuss the remaining properties of remaining periodic properties in the next lecture. Thank you very much.